For this week's project, I wanted to try image interpolation from scratch. So, let's get started. What even is image interpolation? Image interpolation is the process of using known intensity values to estimate intensity values at unknown locations. Put simply, you use an existing position to estimate where it should be on another location. So this is used for things like zoom operations, image projection, so making images bigger, repairing broken or corrupted images, so good images. So whenever you go to the movie theater and you see the movie playing on the giant screen, that's image interpolation. That's not the original size of the image, that's just the projected position of these values. So that's what I'm attempting to create from scratch. So there are three techniques for image interpolation. There's many others, but for this video we're going to look at three. The first is the nearest neighbor interpolation. This is the simplest technique. It uses the nearest pixel only. It's a simple and fast technique, but it results in distortion of features, especially on straight edges. So basically you don't get as good of a result as you would, but it's much simpler and much faster computationally. The second technique is bilinear interpolation. So you use 4 nearest neighbors. The closer to a pixel, the higher the weight is assigned. You use the average weight method, you get a better result. Again, it's not as good though. Like, you're not going to get crystal clear image projection, you're still going to see some distortion. The last is bicubic interpolation. You use 16 nearest neighbors, so a 4x4 neighborhood, and you fit a series of four polynomials each with 4 control points. It gives better results with fewer interpolation artifacts, but is more computationally demanding. So amongst these techniques, this one yields the best results, but it is the most complex. It does also have the most computationally intensive demands than the other two, but its interpolation is way better. So this is the original image for this project. It's a picture of a young woman, good quality picture. Let's look at the nearest neighbor results. So using the nearest neighbor technique, this is the image projection. So basically what I did was to make the image smaller and then project it again to simulate image interpolation. As you can see, you can still make out that this is very similar to the original image, but a lot of the finer details are gone. You don't see the crisp detail, no straight edges, nothing is crisp. You can clearly see the pixelated values everywhere. Let's look at bilinear interpolation. Much better than the nearest neighbor. It's much closer to the original image, but it's still blurry. It's still not clear. It's not as good. As you can see, a lot of the finer details are captured, but a lot are still missing. There's like a hazy overglow over the image, and that means a lot of the sharp features aren't captured at all. Last but not least, let's look at the results of bicubic interpolation. So this is by far the best one. This looks the most like the original image. You can still somewhat see some image artifacts. It's still not 100% like the original image. That's because there's way more image interpolation techniques. But for this project, I have only looked at 3. But of those 3, this is definitely the best one. It has the least amount of fuzziness, has the least amount of pixelation going around. You can see the most amount of detail. So these are the results of this project. With that being said, now let's look at the actual code. For this project, I wanted to use OpenCV to show you how you can use that library, but to also do the image interpolation from scratch. So here, we're making the original image 4 times smaller. And now let's look at the nearest neighbor interpolation from scratch. So the very first thing is that we want to create a NumPy matrix of the original size of the image. This is just an empty matrix that we fill later. We loop through that matrix and then we find the nearest neighbor. And then we just assign the nearest pixel value to the rescaled image. And then we just save the results. This is how you can do it using OpenCV. You use the resize method, and all you have to do is just set the interpolation value to be CV to inter nearest. Now let's look at bilinear interpolation from scratch. Again, we create an empty matrix, and then we calculate scaling factors. We need those in order to find the position relative on the new image relative to the old image. So we get the coordinates of the top left as well as the bottom right pixels. And then we calculate the distance between them. And this allows us to retrieve pixel values for the four corners of each image. And then we compute the weighted average of each of these neighbors. We use that distance and the retrieved pixel values in order to calculate a weighted average overall, and then we assign that to the rescaled image. So overall, it's more complex than nearest neighbor by far, but it's not terribly complex. To do OpenCV, all you have to do is just change the interpolation option to be linear. Now let's look at bicubic interpolation from scratch. This is by far the most complex and the most computationally intensive of the three, but it does yield the best results. So this is its implementation from scratch. The first thing to do is to create a method to compute the cubic kernel. So this cubic kernel is what we use in the end to actually to create that polynomial function all the way at the end. So then we define this method right here. We get the absolute value of x, and depending on where it is, we create a polynomial for it. And then that's what we use in the end of our bicubic interpolation. This is the main bicubic interpolation method. We rescale the image using the technique. So depending if it's grayscale or colored, we need to change the channel's value. And then we get the original height and width of the image, and then what we need to output it to. We create an empty matrix depending on if it's a grayscale or colored image, and then we calculate a scaling factor. So this is the inverse of the original scaling factor, and then we loop through that entire matrix. We get the coordinates like we did in bilinear, but here we do a bit more complex operations, and then we need to accumulate the results in the end. So this is a 4-nested loop because we need to get 16 points for every single pixel. We get the nearest coordinates of this plane, so we're going in the z direction as well. We need to handle some boundary conditions, and in the end, this is where we use the cubic kernel to calculate the weight, and then we assign that weight depending on if it's grayscale or colored. That's what we output that's what we use the output matrix value to be, and then we just save that. We save this as the image. We blow it up and save it, and depending on the scaling factor we use, this will affect the quality of the image overall. So this is a lot of code, but if you use OpenCV, all you have to do is just select that specific function as well. That's it. There's nothing much more to it. So overall, I hope you've enjoyed this project. This project aims to take a look from behind the scenes of how some of these OpenCV methods are actually implemented. Obviously, they do way more optimization and more complex calculation to get better results, but this allows you to see how much work just goes behind simply just changing a certain option. So bicubic, as you can see, was way more complex than the nearest neighbor. So overall, I hope you enjoyed the project, and like, comment, and subscribe. And if you have any ideas for future projects for me to do, please let me know.